Good morning. We're going to pick up where we left off last class. So this is still section 4.1. We're looking at exponential functions. We had gotten to the compound interest slide, and I kind of rushed through towards the end there, so I want to make sure we go back, take some time on this, and then we'll do an example with it. Before we do that, though, I did move the homework, the upcoming homework. It's like 4.1 to 4.4. For right now, I've moved it to Wednesday. I may even move it further back, depending on how far we get today and tomorrow. But the next couple of sections are actually a little bit short, so we might actually get to 4.4 by Wednesday. If not, then I'll push it back even a couple more days. Okay, but it's definitely not due tonight. It will be due Wednesday at the earliest. Any questions about anything right now? All right. Well, let's go ahead and jump back into this section then. All right, so like I said, compound interest is one of our practical applications of these exponential functions. And so the function here is given. And so we went through last time, what do each of these variables actually mean? And so the first one here, the A of t, that's just the accumulated amount after a certain number of years. Okay, so t is going to represent our number of years. A of t is just the amount after that many years. P is going to be the principal, and anytime you think principal, that's going to be your starting amount. Okay, so how much money are you actually starting with? How much money are you investing? That's going to be your principal. The rate in this case is going to be given as a percentage. It's going to be an interest rate. We always want to change that percent to a decimal, okay, before we actually do any calculations with it. So whenever we plug it into our formula for this R right here, just make sure we always change it to a decimal first. N is going to be the number of times we compound our interest each year. So that's when we did this little table down here, and I know it may be difficult to see. We talked about some keywords that you might see in the problem that would tell you what your N value is. Okay, so we said one of those keywords was going to be annually. And so if you see the word annually, that means we're compounding one time per year. If you see the word semi-annually, that means we're going to be compounding 2 times per year. Quarterly would mean we're compounding 4 times per year. Monthly would be 12 times per year. And then daily is always going to be 365 days per year. Okay, so these are going to be the N values that we're going to substitute into our formula. And notice there's 2 different N's that we're going to be replacing here. Okay, but both of those N's will be replaced with these values depending on what keyword you see in the problem. Okay. Give me 1 second because that just shut off for some reason. But any questions there about any of those keywords? All right. So let's take a look at an example then and see if we can set up the equation. All right, so we've got a sum of $1,000 being invested at an interest rate of 12% per year. We want to find the amounts in that account after 3 years, and we're going to do this 5 different ways. You might not do all of them, but I want to try a couple at least. So we're going to do annually, semi-annually, quarterly, monthly, and daily. So each one of those is going to be calculated differently. If we look at this one, right, we know we're looking for the total amount after a certain amount of time, so that's going to be A of t. So that's what we're trying to find. Now, according to our formula, what are we going to start with? Good, right? $1,000 is our principal. That's how much we're starting with this time. So that's what's going to go first in our formula here. So we're starting with 1,000. Okay, the next thing in our formula is always going to be 1 plus. Okay, so regardless of the problem, always 1 plus. Now we need our rate over the N value, right? So let's talk about the rate first. So what is our rate this time? Good, right? So it's 12%, and we said we want to change that to a decimal, and the way we change that to a decimal is we take that 12, we move the decimal 2 places to the left, and so that's what's going to give us 0.12 as our rate this time. Then we need our N value. So if we look, the first one we're asked to do is annually. So what's our N value going to be for annually? 1. Good. I'm going to put this over 1. And then our exponent this time is going to be N times T. So what was our N value again? Same N value, so we put 1 again. And then the T value is the number of years. How many years do we have this time? 3. Good. So there's everything substituted into that formula for this particular problem. And again, we're doing annually, which is why our N value this time is going to be a 1. Now we just have to go through and simplify this. Now it's up to you. If you want to do it step by step, we can. If you want to put the whole thing in your calculator, you can. Just be very careful to make sure that you've got parentheses here. Also make sure that your exponent is grouped together so that it does the 1 times 3 together. Otherwise, it's going to raise it to the first and then multiply by 3. Okay, so be careful there. But if we go through this step by step, we do what's in parentheses first. So this is going to give us 1 plus 0.12 divided by 1. That's just going to be 1.12. And then our exponent is 1 times 3, so that's just going to be to the 3rd power. All right, and then at that point, you can definitely go ahead and put it in the calculator. So we've got 1,000 times 1.12 to the 3rd power. And so somebody help me out. Tell me what you get for that. Okay, so we got, all right, so let's see. So Kenneth's got 1728. Anybody get anything other than that? Yes, there we go. Okay, so 1404, and then if we round it this time, because we're dealing with money, what should we round to? Two decimal places, right? Okay, because we're going to round to the nearest cent. And so if we round this one off, that should round to 93 cents this time. So $1,404.93. Anybody not able to get that value there? And so just take your time on these, right? Just make sure you're typing everything in the calculator correctly. That's the big thing on these types of problems. Okay, so get everything substituted in correctly, and then just make sure you enter it correctly into your calculator. Let's do a couple more of these. So this time, let's look at, I'm actually going to do quarterly next. So let's do this one. So we did annually first. Now we're going to do quarterly. So what's going to change if we do this quarterly now? The N value, right? That's all that should change. Everything else is the same. Still have $1,000 for the principal. We still have the 0.12 rate. We're still doing it for 3 years. So N is the only thing that's going to change here. What will the new N value be if we're going to do this quarterly? 4, right? So I'm going to come in here and I'm going to say, well, still 1,000 times 1 plus 0.12 divided by, and now instead of a 1, we want to use 4 for the N value because we're compounding quarterly. And then in the exponent, same thing. We need that same N value, 4 again, but then our time is still 3. Now again, we can go through and simplify first if you want, or you can put the whole thing right in the calculator. I'm going to go ahead and clean up what's in parentheses here. 0.12 divided by 4 is 0.03. Add that to 1, we get 1.03. And then 4 times 3 in the exponent should be 12. And so now if we do that, So Sarah's got 1573.2. I got something different from that. 1425.76. That's what I got. Okay, good, right? So just double check there and make sure, right? It's 1,000, and then we've got 1.03 to the 12th power. And in this case, if you want to, right, you could always do the 1.03 to the 12th first and then multiply that by 1,000 just to be safe. Make sure it's doing the exponent first. But it should come out to $1,425.76. Okay. Okay. All right. So anybody still not able to get that value now? And so just always be careful, right? If we change one in value, we have to change both, right? Because they're going to always be the same number there. Any questions on that one now? All right, so let's do daily to get practice with one more. So again, we're doing A of t. The 1,000 is not going to change. 1 plus rate not going to change. What's the n value going to be this time? Right. So daily is 365 times. And that means our n value in the exponent is also going to be 365 and then times 3 years again. Yeah, so just be careful there, right? So whenever it's daily, there's 365 days in a year, and so we're always going to use 360. And like I said, don't worry, it doesn't matter if it's a leap year or whatever, right? It's always going to be 365 if it's daily. All right. Now this time, right, cleaning this up isn't going to be as easy as what we got over here. So I would probably just put the whole thing in the calculator. Again, just make sure when you do that, that you're grouping that exponent together somehow, so that it's that you want to multiply what's in the exponent first. Okay, and so Anthony says 1433.24. That's what I got also. Anybody not able to get that value? Now, let's look at these values, right, that we ended up getting here and just kind of think about what's happening. So when we did this annually, meaning we were compounding our interest one time per year, we ended up with a value of $1,404.93. Now, once we went to quarterly, what happened to our value? It increased, right? When we went to daily, it increased again. So the more times we compound our interest, even keeping the interest rate the same, okay, the more we're going to increase. But notice here, there's not a huge difference between $1,404 and $1,433, right? We're only looking at, $28 and something difference between the two, even over a 3-year period. So don't think that it's to make it balloon really fast, right? It's not going to grow at an exponential rate just because we're compounding more often. If all of these other things stay the same, the interest rate, the amount of time, and what we're starting with, you're going to get slightly different values, and these will be higher the more times you're compounding, okay, but it's not going to be a significant amount unless the amount we're investing is also very significant, okay? Any questions on that one? All right, so there's our compound interest. Now we're going to move on on to section 4.2, which is what we call the natural exponential function. All right, so the last section was about just general exponential functions, right? We could have a base of 2, a base of 3, a base of 4, whatever. We always want to talk about positive bases. We were always using integer values there, right? Okay, now we're going to look at a different base of our exponential function that we call the natural base. Okay, and so that's why we call this one the natural exponential function. And so this is what the natural exponential function looks like. So if we have something that's f of x is equal to e to the x, our base this time is e, and sometimes you'll hear this referred to as the exponential function because this is probably the most common, right? It's the one that occurs in nature the most often, which is why we call it the natural exponential function. So if you see the exponential function, just know this is the one they're referring to. Now, this base of e, this e is actually a number, okay? Kind of like pi is actually a number, even though it's a symbol, it represents a number. Same thing with e. So on your calculators, okay, as long as you got a scientific calculator or a graphing calculator, you should have an e key on there. On my calculator, the TI-83, I'll actually put my calculator up here so you can see it. Mine's right above the natural log key, which is over here on the left, and it's kind of hard to see because it's so tiny, but there's a little e to the x up here. There's also an e above my division key. Either one of those will give me the same value, okay? So it really matters. If I do second and the ln key to get e to the x, then I just have to make sure I actually put a 1 in there to say e to the first power, and then it'll give me a value, okay? And so you can see in this case, we get 2.71828, and this is an irrational number. It's going to continue on forever and ever and ever. It actually does not repeat, right? Even though it might look like it does there. If you go out further, there's no repetition of that decimal. Okay, so this is still an irrational number, and usually we'll just say it's about 2.718 something. Okay, so if you keep 3 decimal places there for e, that's kind of how we round that one off. But just keep in mind, anytime you see e, it's not a variable, it is actually a number, and it represents this number right here. Now, if that's the case, right, if this is our, and we're looking at e to the x, what do you think the graph of that function is going to look like then? Think about some of the functions we looked at last week, right? We looked at like 2 to the x, 3 to the x. Think about what those graphs look like. And this one's, 2.7 something to the x. So it should be somewhere in between those two values. But what did those graphs look like for 2 to the x and 3 to the x? It's a J, right? So these were J-shaped curves, and it's going to be the same thing here, right? So since this value of E is somewhere between 2 and 3, it's still bigger than 1, and we said anytime you have a base bigger than 1, you should end up with a J-shaped curve. So this one's going to just be a J-shaped curve. It's going to be somewhere steepness-wise between 2 to the x and 3 to the x because it's 2.71, right? Okay, but in this case, just know we have a J-shaped curve. Still going to have a lot of those same behaviors. It's going to go through the point 0, 1 on the y-axis. Still going to have a horizontal asymptote along the x-axis at y equals 0. Okay, but this is just going to be a J-shaped curve. Any questions on e to the x right now? And we'll spend a lot more time with the graphs, right? So we'll look at some of those. First, let's just do some calculations with e, just to make sure we can do that in our calculator. So we got e to the 3rd power. So again, find your E key. And we want to raise E to the third power this time. And we'll just round this. Let's go with 4 decimal places. Tell me what you get. Well, it says 5, but okay, so 20.0855. Good. And if we follow directions, it says 5, right? So that would be a 4 after that if we go to 5 decimal places. Any questions on how we got that? Okay, so again, the next one we can put in there just as it's written, so 2 times e to the negative 0.53. And so let's do this to 5 since that's what the directions say this time. Good. All right. 1.77, oops, sorry, 1.1771 if we round that one off. Okay. Any questions on how we got that? All right, and the last one, just e to the 4.8. So we got 121.5104. And then it looks like the 1, there's a 7, right? So that would round that value up to a 2. Good. So 51042 in this case if we round it up. All right. Any questions on that one now? So just make sure whenever you're doing problems like this, make sure you're actually using the E key to get that value rather than just rounding it off to 2.7 something, because otherwise, that's going to make a pretty big difference in what these decimal values are. Okay, so just use the E key. All right. So now let's look at some graphs. And so we're going to sketch the graph for each of these functions, and we'll talk about domain, range, and asymptotes. All right, so first of all, just y equals e to the x. I'm going to sketch that over here. So we said it should just be a basic J-shaped curve. It should still go through the point 0, 1, and it should still have a horizontal asymptote at y equals 0. So our basic e to the x graph is going to look something like that. Okay, so there's our parent function. That's what we're trying to transform this time. So if we look at the first one here, e to the negative x, what is that going to do to our graph? Okay, so it is going to be a reflection, right? And so now we just need to know, is it a reflection over the x-axis or a reflection of the y-axis? Since the negative is up here with the x this time, good. It's actually going to reflect it over the y-axis. Good. So we got reflection over y-axis. So now let's think about what that graph would look like if I were just to reflect it over the y-axis. We got f of x. So, is anything going to change about my y-intercept? No, right? So the y-intercept's still going to be at 0, 1. And now if I just take all of this and I reflect it, right, that means this piece is going to be over here, and this piece is going to be over here now. And so now, instead of being a J-shaped curve, it becomes what? Good. So now we just have an L-shaped curve that looks like this. Still has the y-intercept at 0, 1. Okay, now what's the horizontal asymptote going to be for this one? Good, right? So still, even though it's approaching on the other side, it's still y equals 0 for that horizontal asymptote, right? So this time over here, we were approaching as we went towards negative infinity. This time we're approaching as we go towards positive infinity, but it's still the horizontal line y equals 0 for our asymptote. Let's look at domain and range. What's the domain for this function going to be? Good. So all real numbers, negative infinity, positive infinity. So that's domain. What about the range? So this time it's going to be 0 to positive infinity, because remember we have that asymptote at 0. Everything in terms of the y is above the x-axis here, so it's all positive. So it's going to be from 0 to infinity, and we don't want to include the 0 because there is an asymptote at 0 this time. Okay. No worries. Any questions on that one now? All right, let's look at the second one. So now we want to think about what transformations are going on with 3 times e to the 0.5x. Okay, so again, thinking about this function here, what transformations are we doing to get that graph? So start with the 3. What's the 3 going to do to our graph? Okay, good. So it does become the y-intercept in this case, right? Because the 3 in general is going to do what to the graph? Stretch it. Stretch it how? Good, vertically. So we have a vertical stretch by a factor of 3. Okay. So remember, anytime you've got a number out front of a function like that that's being multiplied, if it's bigger than 1, it's going to be a vertical stretch, and then we always take the factor here. Now, what's the 0.5 in front of the x going to do to our graph? Good, right? So it's going to be horizontal because it's with the x. And in this case, everything that's horizontal is always backwards, right? So a fraction or a decimal here is actually going to give us a stretch horizontally. And it's going to be by a factor of, what's the factor going to be? So not 0.5 because we want to actually stretch it. So we have to take the reciprocal. So what's the reciprocal of a half? 2, right? So it's actually stretching horizontally by a factor of 2. So just keep that in mind. Whenever you've got something horizontal, stretch or shrink, you're always going to take the reciprocal to get the factor this time. All right, so now let's think about what that graph's going to look like if we do those transformations. So Kenneth gave us one thing already. So we said our y-intercept now, instead of being at 1, should be all the way up at 3, because we're going to stretch that vertically by a factor of 3, and that 1 gets multiplied by 3 here. And let's think about our asymptote, right? Because we have no reflections, no shifts, right? Where is the horizontal asymptote going to be this time? Good. It's still going to be at y equals 0, because even if I take this graph here and I start stretching it out vertically, right, stretching it this way, this doesn't change because stretching 0 still becomes 0. So I'm basically just taking everything up here, I'm pulling it vertically this way, so it's going to stretch it out, and that's why it goes through 3 instead. Now here, though, I'm also still stretching it horizontally, so not a lot's going to change, right? Because if I change it, stretch it vertically by 3 and horizontally by 2, it's still going to have almost the same basic shape that we would have had before. I just need to make sure that I'm going through that point at 3 instead. So it's going to look more like that now. And let's get our domain and range. So what's the domain going to be for this one? Good. Still all real numbers. So negative infinity to positive infinity. And the range is what? Good. So 0, positive infinity. Again, not including the 0 because there is that horizontal asymptote there, but everything on our graph here is above the x-axis, so we're only including those positive values in our range. Any questions on that one now? Just keep in mind, right, you have access to Desmos, you have access hopefully to a graphing calculator, but use those things to your advantage. Graph the actual function, make sure that it matches everything that we got here, because you don't necessarily have to sketch this by hand. This is more the information I would be looking for maybe on a test or something, is can you identify that stuff? Okay, but use the graph to kind of help you out. Anybody need more time on that one? All right. All right. This is always one of my favorite problems, and it's even more so right now because it's pertinent. Okay, so an infectious disease begins to spread in a small city of population 10,000. After T days, the number of people who have succumbed to the virus is modeled by the function, okay, that's given there, right? And there's a lot going on there. So we got 10,000 divided by 5 plus 1,245 times e to the negative 0.97t, right? So a pretty complex function. First thing we're asked to find is how many infected people are there initially, right? And by initially, they mean when this thing all started at time t equals 0, what was the infected people rate, right? So how many people were actually infected then? So how are we going to find that? Good, right? So they give us at time t equals 0. So we're going to plug in 0 for our t value into this function right up here, right? So I'm going to try to do that work over here. We got v of 0 this time. We still got 10,000 in the numerator, divided by 5 plus 1,245 times e to the negative 0.97 times 0. So again, all we're doing is we're taking this function here, plugging in 0 for that t value, and that's what we're going to get. So now we just need to go through and actually simplify this, right, and see what we get. Now this one I think we can actually probably do mostly by hand. So start with your exponent here. What's negative 0.97 times 0? 0, right? And what's e to the 0 power? Just 1, because anything to the 0 is always going to give you a 1. So now this whole thing here just becomes a 1. And so what I have is 10,000 divided by 5 plus 1,245 times 1. Well, now I can just go ahead and add what's in the denominator then. So we have 10,000 divided by, what are we going to get in the denominator? Okay, so we have 1,245 plus 5, right? And so what should that give us? Good. Right, so 1,250. And then we just have to do our division, right? So what's 10,000 divided by 1,250? Good. So it should just be 8. So what that tells us here says how many people were infected. So initially in that town, there were 8 people infected. Any questions on how we got that? All right, so I want you to try the second part here. So they're asking us to find the number infected after 1 day, 2 days, and 5 days. Okay, so we're going to end up basically with a table here where our t values are 1, 2, and 5, and we're looking for the number of people infected at each of those times. So start by just plugging in the 1 for our t, simplifying all that, see what you get, then try the 2, then try the 5, and give you some time to work on that, and then we'll come back and check those answers. All right, has anybody at least gotten 1 day yet? Good. Okay, so 1 day should get 21 people infected there. Anybody that finished that part and not actually get that answer? Any questions about how we got that answer? Has anybody finished 2 yet? Okay. So Anthony says 57. Naomi's got 54. I think I got 54 also when I did it. So it could be like a rounding thing. Maybe you didn't keep as many decimal places here or something, right? Because you're in the ballpark, Anthony. So I would just go back and just maybe keep a little bit more in terms of what you get here. But I think 54 is more accurate. Now, notice here, in all of these, we're rounding to what? Whole numbers, right? And why are we rounding to whole numbers? Because it's people, right? Okay, there's no half a person, right? We don't want to. You can't say that half of a person was infected or something like that. That wouldn't make much sense. Okay, so we're always going to round to the nearest whole number because this V of t here is the number of people that are actually infected, right? So then at 5, anybody get that one yet? Good. So 678. Okay. And just notice here, right? Just within 5 days, we went from having 8 people initially infected all the way up to 678 people that are now infected, right? Okay, so that number grew pretty rapidly after the initial starting point. Now, here's what I want us to think about. What do you think this graph is going to look like? So without actually graphing it yet, right? And we are going to do that, and we'll look at it together. Okay, but what do you think this is actually going to look like graphically? Steep, right? Okay, that's a good way to put it. Okay, so we know in this case, right, we started with 8 people. After 1 day, it grew to 21 people. Another day later, it's already at 54. And then 5 days, right, we're all the way up at 678 people, right? So it is going to be a pretty steep curve when we graph it. All right. Anything else about it you might be able to describe? Okay, so maybe a J shape, right? Because we've looked at some exponential functions already, okay, that had that J-shaped curve that as we went past 0, right, it started to grow in that exponential nature, and we got that J-shaped curve, right? So that kind of makes sense. Now, here's what I want you to think about just in terms of the context of the problem right now. All of the ones we've done so far, right, our range was like from 0 to infinity. Right, we started and said, okay, the lowest amount we could potentially have is 0, which would be true here, right? You can't have less than 0 people infected. But then would we be able to go all the way to infinity this time? Why not? There's a population to the city, right? So we know we can't go to infinity because there's only 10,000 people in the town to begin with. So at most, right, we know that we're going to have to cap ourselves at that. Now, here's what I want you to think about. When we graph this, do you think that our range then would be from 0 to 10,000? Or do you think maybe it's something different? An answer to that yet, that's fine. If it can eventually infect everyone, then yes. Okay, so that's a good point, right? So if everybody eventually gets it, then yeah, right, that's probably what's going to end up happening. Do you think, let's just think most viruses right now, right? Do you think that everybody ends up being infected by the virus in most cases? Probably not, right? Maybe there's a vaccine created, maybe something else happens, right? Okay, so it is possible that this thing doesn't actually infect everybody in the town. And so let's take a look at the graph and see what's actually happening here. I'm going to put this in Desmos and I'll share that with you. 10,000 divided by 1245e to the negative 0.97. All right. Let's share this. All right, so there's what my graph looks like, right? Just in a normal window from negative 10 to 10. So what do you think we might want to do with this graph to maybe see exactly what's happening then? All right, so we need to zoom out, right? So specifically, what do you want to set your window at? So I'm going to try to do it manually rather than zooming out. Just keep in mind here, the x-axis is like the t, right? So that's the time, that's the number of days. And then our v of t, the y-axis, is going to represent the number of infected people. So what values would you want to use there for the x and y axis? All right, so think about what we just said in terms of, the people infected, the V of T value, the absolute biggest, right? 10,000 is the absolute biggest it could possibly be, right? So we know if we set it to 10,000, we're definitely fine, right? So let's go ahead and just change that. We can always readjust if we need to. So I'm going to change my y-axis now, leave my min the same, but I'm going to adjust this to 10,000. That's what the graph looks like if I adjust it to 10,000. What do you notice? It actually starts leveling out at 2,000 instead, right? And so context-wise, what would be some reasons why it wouldn't go all the way to 10,000 and it would start to level out at 2,000 instead? Okay, so in terms of the actual equation that's given, right, I'll tell you why. It's this 1,000 right here, and we're dividing by this 5 down here. 10,000 divided by 5 is what gives us the 2,000, because the smallest that this thing right here is ever going to get is going to be 0. So we have 10,000 divided by 5 plus 0 as our limit, basically, as the maximum value we could hit. And so that's what gives us the 2,000. But just contextually, right, real world wise, think about what's going on right now. What is it that's causing that thing to possibly level out at 2,000 going all the way to 10,000? Okay, maybe it becomes contained, right? Okay, so you start quarantining people, so you are infected, they can't spread it to other people, right? That's one thing. Right? Maybe you've put in mitigation factors like we have right now in the US, right? Where we're asking people to use social distancing, we're asking people to self-isolate, stay at home, things like that, right? That's going to slow that curve down so that it doesn't actually infect every single person all at one time, right? Okay, so it is possible, right, of those things. Vaccines are another thing, right? So if we do come up with a vaccine, also level that thing out, because then the people that get the vaccine hopefully wouldn't actually catch the virus, right? And that would level it out also. So just keep in mind, right? Again, you've heard this, like, let's slow the curve, right? Let's level it out. That's exactly what you're seeing in this graph. Is we're trying to level this curve by putting all these strategies in place so that it doesn't balloon to 10,000 and infect everybody, right? We're kind of slowing it down a little bit, slowing that growth. Okay. Any questions on that one? All right, so that's where we'll stop for today. I do have one more example in that section, so we'll finish that up and then we'll move on to the next section. Again, the earliest the homework's going to be due is going to be Wednesday night at this point, okay? But continue to work on that. Send me questions as you've got them. I will see you guys tomorrow. Have a good afternoon.